Dr. Hargraves has written articles and made presentations about the Liquid Fluoride Thorium Reactor, or LIFTR, as we affectionately call it, and energy cheaper than coal, the only realistic way to dissuade nations from burning fossil fuels. His presentation, Aim High, about the technology and social benefits of LIFTR has been presented to audiences at Institute for Lifelong Education at Dartmouth College, Thayer School of Engineering, Brown University, Columbia Earth Institute, Williams College, Royal Institution, the Thorium Energy Alliance, the International Thorium Energy Association, Google at Mountain View in both 2009 and 2010, the American Nuclear Society, the President's Blue Ribbon Commission of America's Nuclear Future, and the Chinese Academy of Sciences. With co-author Ralph Moore, he has written articles for the American Physical Society Forum on Physics and Society, Liquid Fuel Nuclear Reactors, that was January 2011, and American Scientist, Liquid Fluoride Thorium Reactors, July 2010. Robert is a study leader for energy policy at Dartmouth Iliad. He was Chief Information Officer at Boston Scientific Corporation and previously a senior consultant with Arthur D. Little. He founded software firm DTSS Incorporated while at Dartmouth College, where he was assistant professor of mathematics and associate director of the Computation Center. He graduated from Brown University with a PhD in physics in 1967 and Dartmouth College, AB Mathematics and Physics in 1961. It is with appreciation that we welcome Robert to speak to us here today. Thank you.
Well, besides the climate crisis, we have an economic crisis. Here's an example of it in India. You can look at that picture and see that the Indian economy is not doing particularly well. You'll also notice that they are collecting biofuels, which is not really an environmentally friendly activity. The other thing to notice is that that's not a great source of energy. And another thing to notice is that these are all women who are quite underemployed in this country. So there are a lot of problems that are encapsulated in this photo that we want to try to address. First thing to notice is government debts. It's not just the U.S. that has a debt crisis. It's many of the nations on Earth have a growing debt compared to their gross domestic product. It's not just us. How do we solve that problem? We have the risk of default on the debt. We have a potential risk of inflation if we all print more money. GDP might contract, destruction of people's savings, and the collapse of the welfare state in Europe. There are solutions that are proposed. The conservatives and Republicans generally say, let's cut back on spending. That's the way to solve the debt crisis. The more liberal economists would say, well, let's spend more money and get us out of this situation by sparking economic growth with deficit spending. Or perhaps we should devalue the dollar and export more, but that doesn't work if all the countries do that. That's a zero-sum game. So what can you do instead? One example is productivity growth. And you all in the IT industry should remember the Y2K crisis. During that crisis, which was caused by people worrying about the two-digit year number not being enough and causing failures in control systems and so on, many CEOs of Fortune 500 companies were scared. So they invested tons of money in products like Google's system or SAP for enterprise-wide software to control everything from personnel to purchasing to production control, bills of materials, the whole package in multiple locations, multiple currencies. In fact, that investment paid off. It did increase GDP. It's one of the factors that was responsible for the growth in economic productivity in the U.S. in the early part of this century. So, what about the idea of productivity growth through cheap energy instead of new software? Cheap energy can make a big difference. We'll talk about that. Meanwhile, we have a few crises sitting in front of us. We have the iconic polar bear symbolizing global warming. We have world population growing from perhaps 7 billion today to 9 or more. We're running out of food. The fish in the ocean are largely depleted, at least the large ones that we like to eat. And don't forget, we have wars over natural resources. This is a picture of a war in Kuwait where Iraq invaded for oil and then burned the oil wells on the way out. So the competition for natural resources, particularly energy, is a problem. Coal emissions in the U.S., according to the Environmental Protection Agency and according to the local Cambridge Clean Air Task Force group, says that there are 13,000 deaths a year from respiratory illnesses caused by inhalation of small particulates, 2.5 microns in diameter and less. There are perhaps 500,000 or 1 million such deaths in China and other places where the particulates are even larger. In the case of global warming, my concern mostly is food production. This is an example of the Ranbuk Glacier in India, decades apart. In one case, we had lots of ice flowing down, and the other case is nearly dry. The glaciers are the source of summer melt water that enables agriculture to thrive year-round in these places. The loss of this kind of water supply is a threat to food supply worldwide. That's my biggest take on global warming. This is a chart of data that was compiled by the CIA. On the horizontal axis are for each nation in the picture the number of children per woman births on the average, and on the vertical axis the gross domestic product per capita, which is very closely related to income. One of the things you should notice just looking at it instantly is that the stable replacement rate of about 2.2 births per woman is only exceeded in the poorest countries in the world. Those countries that are relatively well off from a GDP per capita point of view have a sustainable or diminishing birth rate. So prosperity is an important stabilizer for population. If we look closely here, we notice that that occurs at somewhere around $7,500 per year gross domestic product per capita. That's the number we'd like to get to. If we could do that, it appears we could really stabilize the Earth's population. Why? Because women who are in prosperous countries have time to get off their chores, time to relax, time to go to school, time to get jobs, time to have money of their own and exert the independence they need to control births. Prosperity has cut the birth rate. Prosperity is also largely dependent upon energy. Now, energy is not the only component to make a prosperous nation. We need good government, we need the rule of law, we need education, but we also critically need energy, and specifically we need electric energy, the kind of power you need for refrigeration, for commerce, for transportation, for safety, for machine tools. Everything depends upon that rather useful form of energy, electric power. And here it's about, again, about 2,000 kilowatt hours per capita seems to be a number that is associated with the level of prosperity needed to control population. For comparison, the U.S. is off the chart here. We're at about 12,000 kilowatt hours per person, Canada 14,000, and occasional countries have even more electric consumption. But somewhere around 2,000 kilowatt hours or 600 watts average power per person seems to be a number that suggests achieving the prosperity for stable population. The other thing to notice is that prosperity depends upon cheap energy. This is a Wall Street Journal chart, and The arrows pointing down to the vertical bars indicate when we've had recessions, and there's an indication that when oil prices spike, there's a strong correlation with diminished economic performance. Several economists try to model the economic behavior as a function of labor and capital and energy and so on. And their conclusions are that if you were to take a big world economy and inject for free about $1 worth of energy in the form of oil into it, you can increase the productivity of the whole economy by about 5 to 1. We still have cheap oil. It can't stay cheap, though. Here's the total investments of the major oil companies over the last 10 years or so. They've quintupled. So if you're spending that much money to explore for new oil, the prices have only got to go up. Now, developing nations know full well that electric power and energy are critical to their economic development. And so they are desperately seeking to get new energy sources. Coal plants. There are something like 1,400 gigawatts of coal plants in production around the world today. And although we kind of think in the U.S. we are diminishing that number as we pass laws and the coal plants shut here, some of them, the number of coal plants worldwide is under planning is going to double. It's going to be another 1,400 watts of power, doubling CO2 emissions. So that's the reality of the projections worldwide. What we do in the U.S. is not so important compared to what the developing nations are going to do. A lot of people say, well, we ought to pass carbon taxes and get the developing nations to not burn so much energy. But the developing nations like China say, wait a minute, the US and the OECD nations gained their prosperity by cheap energy from burning coal. Now it's our turn. How can you say that you achieved your prosperity and we can't? Here's this CO2 emissions per capita of the United States, a little over 1,000 tons per person. China says, well, we've only done 76 tons. When we get to 1,000, we'll talk about it. And that same story will be repeated in India, Indonesia, and so on. Economics is a powerful force. I like Fareed Zakaria. He's got a book, and he tries to point out the importance of economics. And a very mundane thing has changed economics and trade over the last few decades, and that's the container. The container ship has made world commerce possible inexpensively, without pilferage, in a standardized form. That trade takes place between a whole network of 250 nations. So the occasional bilateral treaty we sign to stop some sort of behavior we don't like about energy doesn't matter much. Economics always works around these things. Economics is the most powerful force, not politics. We need energy cheaper than coal. We tried politics to contain CO2, but nations resist carbon taxes. Even a wealthy nation like the United States will not pass a carbon tax. And yet, we have conferences where people go and talk about how to have a political agreement to pass carbon taxes. And here are all some of the recent failed conferences that led nowhere, and yet we keep trying to do that again. We need energy cheaper than coal. That's the only way we can stop people from burning coal, provide them with a more attractive and more economical alternative. A lot of people say, well, why don't we just cut back on our power use? We're gluttons here. We're using too much energy, and perhaps we are. In the U.S., we generate and use about 434 gigawatts of power on the average throughout the year. So let's suppose that we are really good. We cut back our electric power use to half of that, and then the rest of the nations in the world who want to achieve that good standard of living we have in the U.S. also achieve that level of use per capita. That's the projected electric power consumption for the world if that scenario I described is true. So again, what we do in the U.S. is important a little bit, but what the Earth depends on mostly is what the rest of the world does, because there are so many people there. We need energy cheaper than coal, again. Now, in the book, I went through a little scenario to do a very crude model of the costs of electric power from various sources, and this is going to summarize these things. I break costs into three components: capital cost recovery for the investment in the power plant, the fuel it takes, and the operations cost, and so on. Now, given an investment in a power plant like a coal power plant, a brand new one costs on the order of $2.80 for capital investment for every watt of capacity that coal plant will have. So we want to convert that capital cost to the expense of recovering that capital. So we want to know what is the equivalent payment to achieve that $2.08 investment. It's and you have to learn a little bit about present value if you haven't done that. The question is, would I like $1,000 now, or would I like a penny an hour for the next 40 years? The answer to that depends upon the discount rate you choose, and people can argue about that. I picked in this example 8%, but you can do the math any way you like. And I also picked a lifetime for most things of 40 years. In the case of coal plants and nuclear power plants, I picked a capacity factor, that is the time it's running, of 90%. That is, you only get your penny back when the plant's actually running. Doing that, the math is real easy, because $2.8 per watt investment turns out to be 2.8 cents per kilowatt hour, so the math is easy. Okay, we'll use that model. In the lower left of this screen is the only running plant that actually has the ability to capture CO2. It's integrated gasification combined cycle. It's the kind of power plant that burns coal in oxygen instead of air, so there's no nitrogen oxides in the fuel, or no nitrogen. It makes it easy to extract the CO2 from the exhaust stream because it's only water and CO2. But it was very expensive to build. There's only one been built. That cost was about $4.76 per watt just for the capital cost of the plant without storing the CO2 anywhere. Just in the last week, we saw announcements in the MIT Technology Review of two new plants in Louisiana and Canada that have a capital cost of in excess of $9 per watt just to get the CO2 out, not to dispose of it. So carbon capture and storage, which has been touted by the coal companies as clean coal, is economically infeasible. Natural gas, that's the current darling. A couple things here. One is that the capital cost for natural gas power plants is relatively low, on the order of $1 per watt for the capacity. And the fuel right today is relatively cheap. Fuel has been as low as $2 or $3 a million BTUs, and now it's up to $5 about. And of that number, 2.8 cents a kilowatt hour is the contribution to the fuel cost. Again, I just said operations cost in this really simple model are a penny per kilowatt hour. You can do better, but I mean, that's to maintain the generator and the power station and the transformers and all that sort of thing. That's not unreasonable. Again, a simple model. A couple other points, though. One is that most of the gas plants in the U.S. are the ones that were designed to do peaking, that is, to come online fast, speed up the power, and generate electricity. And their efficiency is only about 30%. That is, 30% of the potential thermal energy from burning the fuel is converted into electric power. Whereas the fancier ones that are combined cycle that have the gas turbine for which the turbine heats water to make steam, and a secondary generation scheme are about 60% efficient, much more so, a bit more expensive to run, a lot more conservative of fuel, but they take hours to start up as opposed to minutes. So they're not used for backing up wind power. They're used to, they're used as energy sources. They're pretty good. So that's the situation with natural gas. In the case of wind, it's very hard because you read all the newspapers about how cheap it is and how it keeps dropping. Okay, my approach was to try and find out what the total capital investment was to create a wind farm. Not the wind farm after the subsidies, after the renewable energy credits, after the capital tax write-downs and so on. Try and find out the real cost, the total cost, because it doesn't matter who paid. From a society point of view, from a global point of view, it doesn't matter whether the taxpayer, the ratepayer, the bondholder, whoever put the money in. The question is, as a society, we need to do the right thing because we're talking about a global problem. So find out that total cost if you can. Here's some cost estimates from the EIA, the Energy Information Agency of the Department of Energy, which is usually pretty good. Example was $2.44 a watt. But if you look at the price for the Deepwater Horizon, Deepwater Wind farm off the coast of Rhode Island, that was $7 a watt. Right nearby, Cape Wind is $5.80 per watt. Their capacity factor is only 30% though. So to do the capital cost recovery, remember, we only recover that capital cost when the wind is generating electricity, so you have to divide that capital cost by 0.3 in order to figure that out. Now,
the Cape Wind number for the table on the left?
I think so. I think that's the number I picked. The Cape Wind cost to the utility as a sort of a reasonableness check is in this range. They signed contracts with the utilities in Massachusetts that have an escalation clause, and they'll go up to 24 cents an hour if that happens. So the model is not crazy. It's about right. All right, solar electricity, same idea. Here's that Ivanapo plant at BrightSource is the company. Okay, there again, capital cost recovery, figuring out, in this case, I think I used 25% capacity factor. We have to look in the book. 22 cents a kilowatt hour. Fuel is cheap. Ops are about a penny. Again, here's some examples of capital costs. And here's some examples of contracted power costs, but for which the company sells power to the utilities. So the utilities have been bludgeoned by law and public utilities into purchasing wind power and solar power at the prices, okay, with first priority, and thereafter go and buy natural gas or coal or nuclear or whatever. And here are again some prices that are being paid today, or All Earth is, I don't know if Albion is up and running, All Earth is getting paid 30 cents a kilowatt hour. Remember, coal is about 5.6%, nuclear typically around 6 cents today. Biomass, people say, well, that's renewable, let's try that. Okay, so I looked again at some examples of what these units cost to build, and here are a couple of examples. The fuel, well, delivered to the plant is those numbers. I called up and I found out what it costs to buy tons of wood and put it in the plant, figured out how many BTUs you get out of the wood, and run through the efficiency calculation, and we get fuel costs about 4.7 cents a kilowatt hour. So again, the total 9 cents. So my conclusion is green energy is not cheaper than coal. Here's a summary of what we just covered, right? On the far left, coal. Gas today is a little cheaper than coal. That's why coal use has been diminishing somewhat. And we can probably see that happening for a few more years. But the others are more expensive. Again, the reason the press reports their cheapness is because of unstated subsidies. For example, All Earth Renewables in Vermont, the capital cost of that plant was paid for 30% by the federal government as a tax credit. Not only that, the tax credits by special exemption were not paid at the time the taxes were paid, they were paid upfront, in advance. The state of Vermont gave a 30% capital tax credit to that organization. They get a 2.4 cents per kilowatt hour production tax credit. They get priority on the grid. They can always sell it. The utility must take that power whenever they can, and so on. And they get 30 cents a kilowatt hour for the electricity they do sell. So here's my calculation. Do your own. When you're curious, try and find out what the plant costs, figure out what the capital cost is really, and spread it out over the lifetime and capacity factor of the plant. So here's carbon intensity of the electric power sector worldwide. It hasn't changed a bit. So I say green doesn't work. Can nuclear work? Well, back to nuclear for a second. Alvin Weinberg is the guy who patented, or was co-patenter, of the light water reactor that was used originally in Rickover's submarine and today in all the U.S. power plants and most of the ones worldwide. Rickover was a dynamic and forceful and obnoxious person who managed to get it installed in the submarines and also was tapped by Eisenhower to lead the domestic nuclear power program. And he basically took the same design that was going on an aircraft carrier, put it in Shippingport, Pennsylvania, and that was the seed for all of the power plants, nuclear power plants that were built thereafter. Not only that, the Navy was training admirals and generals, and not generals, admirals and captains, and so on to run these nuclear power plants, and there was a source and supply of skilled nuclear technical people to run the power plants on land. But what about yesterday's solid fuel nuclear reactors? Can they compete with natural gas? Last year, this plant, out of the blue, shut down. They said their operations costs alone were such that they couldn't make money competing against natural gas, which surprises me. I'm still flabbergasted why it was so expensive. At that time, gas was making 4.3 cents electricity. But they couldn't do it even incrementally. They shut the plant. And once you shut it, it's basically gone. Right locally in Vermont, this plant is shutting down at the end of the year. Same argument, they can't make money. So what about the new power plants? The new Generation 3+ plants that Westinghouse is now building, 2 in Georgia and 2 in the Carolinas. That plant costs $6 per watt of capacity. So it looks to me like it's going to generate electric power somewhere around 8 cents a kilowatt hour. Well, remember coal was about 5.6, so that's kind of tough. But that doesn't look too promising yet, unless we can get the cost of those plants down, which, by the way, China is. Westinghouse is building those same plants in China, and their capital costs for the first ones are $2 per watt, not $6. So there's something different about the costs in the U.S. Those of you who like Bill Gates and his investments in TerraPower, remember that he's building a kind of a power plant which is cooled by liquid metal. It's a so-called fast reactor. In the U.S., that program was called Integral Fast Reactor at one time. This is a PricewaterhouseCoopers estimate of the cost of power from that. Gates would say he's aiming to compete with other nuclear power plants, but it's certainly not cheaper than coal. So we need innovation. Let's look at the space program as a source of cost innovation. SpaceX, remember Elon Musk, right? And things like PayPal and SpaceX and Tesla and all those good things. He saw a cost innovation opportunity there because of the shuttle complexity and because of the fact that it used 1970s technology. Now that kind of rings a bell when you think about light water reactors in the United States. So what he did was assemble a small team with low overhead, design an entirely new rocket engine, And do it quickly. Between the time of incorporation and the first rocket flight was only 6 years. The SpaceX Falcon, which is their first product, flew for $443 million. Compared to the NASA estimate for what was going to cost NASA to do it if the government did that project, they're 1.4 to 4 billion. So he's proving that sometimes there is a technical cost innovation opportunity. What about liquid fuel reactors instead of solid fuel reactors? That's my idea. This is a picture of a liquid fuel reactor at Oak Ridge National Laboratory. It's a lot of pipes and a reactor in the sort of top middle on the right a little bit. Oak Ridge started this way back in 1953. This man, Richard Engel, is still a consultant in this area. He, at that time, was putting together a water reactor, that is a heavy water that had dissolved in it a uranium sulfide salt. And it generated electric power as a power plant. Had all the things about stability and so on that we like. They couldn't make it really big enough to generate commercial power. But that was their first adventure in liquid fuel reactors. Thereafter, Weinberg, the guy who invented the light water reactor, also was the director of Oak Ridge and a designer and promoter of the Molten Salt Reactor. So in this case, the liquid was not water, it was salt that was melted. And the salt was a fluoride, fluorides of lithium or beryllium and so on, picked because they have low atomic numbers, and picked because fluorine doesn't absorb neutrons. So they ran a reactor way back in '54 at a red hot temperature. Current reactor is what, 300 degrees centigrade or so? This is quite hot. So proof of concept worked. Later on, after a lot of machinations, they tried to put together one that was going to be more commercially oriented, and that also worked in that time period. Here's kind of how these things work. Here's a chart of the nuclides. The horizontal axis is the atomic number, the number of protons. The vertical axis is the atomic weight, the number of neutrons plus protons. Right in the middle of the chart, you see the U-235 symbol for fission. But if we look up at the top on the 238 line, you can see that uranium-238, which is 96% of all the uranium that's in a power plant reactor today, that uranium, when it absorbs a neutron in that blue arrow symbol, it becomes U-239, which is unstable, and over a period of days decays, finally to become plutonium-239, which is a fissile material. And that fissile material, in turn, fissions and generates heat and power in a reactor. Few people realize that in today's power reactors, we're not only fissioning uranium-235, a third of the power at the end of the fuel cycle is from plutonium. We actually manufacture and burn plutonium right in the solid fuel reactor. In the same scheme, Weinberg and crew pointed out that thorium-232, when irradiated in the same scheme, becomes uranium-233, another fissile material. So there's another avenue, and there's a technical reason why that's sort of convenient, and that is that it can happen at low neutron energies. So that's what's happening. Now we can actually design one of these reactors. So this is a kind of a busy diagram. Okay, so that big yellow circle is meant to be the reactor liquid pot or vessel. And there's a lot of reactions that go on inside there. At the top left is an example of a U-233 fission, which releases neutrons. And those neutrons have a couple of purposes. One is they can promote something like U-238 to become plutonium-239, which can be fissioned and make power. Just as the U-235 or anything else can release neutrons when fissioned and promote 232 thorium to become fissile U-233. So it's a good scheme. It's very relatively inexpensive to construct. It's a highly proliferation resistant scheme of things, more so even than today's reactors. And I'm a fan of this reactor today because I think we can build it relatively inexpensively. It'll run for decades before eventually you have to change the salt. Meanwhile, at the top left, there's a waste separator thing, and some of the fission products like xenon tend to absorb neutrons and impede the reaction. There's a scheme in these kinds of reactors to remove some of the fission products on the fly in the liquid. That's the reason why liquid fuel reactors are attractive, and that is the online quick processing makes them relatively inexpensive. I say that that kind of reactor has the potential, 3 cents per kilowatt hour, to undersell coal. Why? One is, I looked up some estimates that had been done over the past decades for building these kinds of plants, and I just promoted them up to the current, I think, 2012 dollars, and they're in the range of about $2 a watt capital cost recovery. I'm sorry, $2 a watt capital cost, that range. So we're in the ballpark. But the technical reasons have to do with principally the molten fluoride salt. Now, the name of my book starts off with the word thorium because it's a short word, but the real technology key is the liquid fuel form. The fuel, again, is fluorides of lithium and beryllium, fluorine, lithium, and beryllium. Fluorine, lithium, and beryllium all have low atomic numbers. Good moderators. They slow the neutrons down, enabling reactions. Uranium is just dissolved in that molten salt. The salt, of course, has good heat transfer. The reaction's taking place right in it. And so you use that molten salt through a heat exchanger external to the reactor vessel to get the energy out. The whole thing is at atmospheric pressure. There's no, a current light water reactor is pressurized to maybe 150 atmospheres of pressure. So we have a containment building around it just in case that vessel ever explodes somehow. That's never happened, but we still have a safety factor because of the atmospheric pressure of the radioactive materials. Another nice feature of this project is that there's an overheat protection that was designed into the original reactor, and that is there's a pipe you can see that would drain the salt from the reactor vessel itself into a specialized drain tank, and that pipe is plugged with salt that is kept cool with just a fan that blows warm or cool air on it, so that if the thing were to overheat or the electric power were to fail or something of that nature, that freeze plug would just melt and the liquid would drain out into a configuration which can't be critical. There's no propulsive pressure to spew radioactive materials everywhere. We talked about that. And the places are typically designed so that if there was a vessel rupture or pipe rupture or something, the molten salts should spill out and be contained on the floor of the containment. Now, the other point is that it's a low mass project. This original motivation was to design a jet engine for an airplane. So the first reactor design, the second one design, was about 1.4 meters in diameter. It was a beryllium sphere. And they had actually started to build that unit, but they decided not to do it. The motivation was to have Strategic Air Command bombers circling Russia for months at a time, never refueling, powered by these kinds of engines. But eventually the ICBMs we had were able to supplant bombers, and we had nuclear submarines at sea with missiles on them as well. So this project never got much beyond the first prototype experiment on the ground and this design, for which they did build that beryllium sphere and started on it. Compare that to what's going on in China right now. The construction costs are pretty high. This just the dome itself weighs what, 780 tons. So they're moving big pieces of equipment around. And the same thing's going on in Georgia right now, where they're building 2 more power plants. Again, Westinghouse's design. Another point here is that the high temperature of these reactors generates power much more efficiently than the lower temperature of today's pressurized water reactors. So we can actually cut down water use because we're so much more efficient at converting high temperature energy to electric power. And there are versions of this that will actually work with, is that picture complete? Not really, is it? With just air cooling. You can do that. Another thing that's happening right now is a lot of investment at Sandia, particularly in supercritical CO2 turbines. Supercritical CO2 is a kind of a, just think of a liquid of a CO2 and you keep compressing it and it becomes at certain temperature and pressure a kind of a liquid that's compressible. And you can make a very efficient device to convert thermal energy to mechanical energy to generate power with it. Plenty of it around. Well, in the U.S., 500 tons just would run the whole U.S. electric power system for a year. There's plenty of it. My point is that smaller reactors can actually be produced in a production line. Today, we have Boeing aircraft that can make a $200 million aircraft every day. We know how to do that. And making aircraft is sort of the same. We have the same issues about safety, about materials, about thermodynamics. All those things are controlled and result in quality production. The other point here is that if you're producing something on a production line, you have the benefit of the learning curve. The concept here is that when you double the number of units produced, you reduce the unit cost by a certain percentage called the learning ratio. Typically, it's around 20%. In the electronics, high-tech, IT industry, it's been about 50%. Okay, and University of Chicago was conservative in their estimate of 10% in the nuclear industry. But even so, that makes a tremendous difference in cost when we get to producing thousands of units instead of 2 or 3 in a production environment. Again, we could make a certainly a $70 billion a year industry just by producing these units. Suppose we were to do that 1 a day. We could actually cut down by replacing coal plants, the emissions from coal in a period of about 40 years. Okay. So just by replacing them one a day, it's possible to do that. The other things that we can do with high temperatures from these kinds of plants are have new kinds of fuels. So in this example, we're pointing out that although you know about electrolysis to make hydrogen from water, there's also a thermal way to do it by making it very hot and using a couple of catalysts, iodine and sulfur, or copper and chlorine, to create hydrogen, making use of that high temperature, not electric power necessarily. The Honda Clarity you can buy today runs on hydrogen, and there are half a dozen hydrogen cars that you can buy. Hydrogen is okay as a fuel, but you got to compress it in a tank in order to do it, so it doesn't you don't get as much fuel in a car as you would with gasoline. But we can also combine hydrogen with these kind of elements in order to make liquid fuels. George Olah wrote the book about the methanol economy. He's a big promoter of that. Ammonia, surprisingly, is a good fuel. You have to control it. A dimethyl ether, a substitute for diesel fuel. This car has been touring Europe. It's an ammonia-powered car. Suppose you wanted to make carbonaceous fuels like gasoline, because we know how to use that. Where do we get a carbon source that is environmentally friendly, that is, other than getting petroleum out of the ground and burning it. We want a renewable sort of carbon. Where can we get something like that to make these products? One is thought to be taking it out of the air, and people toy with this all the time, and the economics of it are sort of marginal at best. And we're thinking that with really cheap energy from this kind of reactor, it might become economically feasible. But that's, again, a Sandia project, well thought of. Just recently, the Naval Research Laboratories demoed their process for getting CO2 out of seawater rather than air. There's a lot more CO2 per liter in seawater than there is in air, and it makes it an efficient thing. So they've done that and demonstrated how to make fuel. And the point here is that the Navy has experience with nuclear power. They know, and they're looking very deliberately to using this kind of extraction technology to make jet fuel at sea from seawater and nuclear power. And it's not a long way off. We're talking within the decade. This demo skid does work, and has been demonstrated. And in fact, just as a game, they flew a model airplane with the kind of fuel that they manufactured this way. So they're pretty pleased about that. Again, biomass is a source of carbon. You can get it from farming, and if we burn that and it goes into the air, it gets reabsorbed and comes back to the land. So it's a zero impact cycle. But I say, well, don't burn it. Just use it as the source of the carbon atoms you need to make the hydrocarbon fuels. We can make a ton of fuel from 1.7 tons of biomass. Around the world, we use a lot of dung, right, and other sorts of products in order to make fuel. Same idea. Instead of burning them, we could use them as sources for carbon for synthesis. World cattle dung, and people in India collect that, but it's very labor intensive to collect it. I have to point out that we have a collection process here already. So that could be cheap. Back again to the benefits. $1 more energy can spark our economic growth, increase our national productivity, allow tax revenues to rise, maybe improve the government's debt situation. Again, low cost is critical. That's the thing we have to watch all the time. One of the reasons I've been interested in the denatured molten salt reactor is to get that cost down low. In my books and other talks, I've talked about all these benefits from the liquid fuel nuclear reactors. All these things are possible to do, but I'm suggesting now that you kind of put it off until we get the economic case solved. If we can get economic liquid fuel nuclear reactors sold and being produced in mass production, then we got a chance to having them be accepted worldwide and delve into these other opportunities to make use of that inexpensive power. Again, economics always wins in the long run. China's underway. They're building these units. This guy on the left is the son of the former president, Jiang. He's got $350 million allocated to the project, and he has 400 people working on it right now, trying to build a molten salt cooled version, a sort of stair-step version by that date, and a molten salt reactor per se in 2020. Recently, that's been accelerated. Here's a slide that Jiang used in his talk. He points out the crisis in China today, and that is air pollution has become terrible, and the people are very upset about it. So his project has been goaled to go into commercial production in 2024. Of course, China's trying one of everything, right? They've got big dams and 4 kinds of nuclear reactors, and so on, but they're pursuing this intensely today. In the U.S., today's environment, we can't do that. We really cannot. All the rules and regulations of the NRC are very specific to the light water reactors we have. It'd be very difficult. There's no sort of overview of a risk-informed, performance-based regulation. It's comply with this rule. That's how the whole system works. Cost-benefit analyses, which are used even by the EPA, are not used in the NRC. The NRC says safety is paramount. We make no cost-benefit trade-offs. That's the mental attitude going in. The idea of the nuclear quality assurance technology and rules and so on is quipped that every nuclear reactor design has to have a paper that outweighs the reactor. A lot of the quality and insurance issues have been substituted for by paperwork. And so it's quite a difficult thing to do in the U.S. TerraPower, Gates Company, has given up. They're in China trying to do the preliminary work. Of the 4 or 5 ventures that are in the U.S. today trying to do molten salt reactor research, only one says they want to try and do it in the U.S. The EPA, again, has a problem with anything that has to do with radioactivity. There is a sort of a concept of as low as reasonably achievable in terms of limiting radioactive exposures of people. And so the problem with that is it's created a sort of a horror or a fear of radiation that's been endorsed and encapsulated in rules and regulations that make it, again, isn't so much the technology and the limits, but the sort of the attitude of people and so on that makes it hard to get plants licensed or research done. So that's the situation we have in the U.S. Probably this work's going to come to fruition outside the U.S. So that's my summary. Low cost, clean energy from liquid fuel nuclear reactors has 2 great potentials. One is to improve the economics of both the industrialized world that could use a little shot of GDP boost. It could also improve the lifestyle and overcome the poverty of the developing world without increasing pollution, and help us solve our energy and climate crises. Thank you. I'm open to questions.
So, I think what I saw in your presentation here was that you're basing the estimated cost of these liquid salt reactors based on the cost of a bunch of experimental reactors projected out to correct for today's dollar amounts. Are there reasons why we think that a commercially produced reactor, one that is continuously running and not an experimental one, would actually be cheaper to run and cheaper to build than a conventional water nuclear reactor? What are those reasons?
The question is that the presentation cited some old research papers about the costs. Is there any reason to believe that in today's world that might happen to make the cost as low as I suggested? I have one friend who's done a lot of design work, ex-MIT guy, who's spent the last 3 or 4 years designing our nuclear power plant production facility. And he's come up with numbers of 3 to 5 cents per kilowatt hour for a denatured molten salt reactor that is in a design that he's right now still got under wraps. But yeah, I've seen the paper, I've seen the calculation, so it's feasible. Again, it all depends eventually upon what are all the sudden rules and regulations that come into play. If your work is suspended for 2 years while there's a hearing or something of that nature, that drives the costs up very rapidly. So his estimates are in what I would call a rational regulatory environment. So that's what we would have to achieve as well in order to get those costs in line.
And I have a related question, which is, I think you agree that in the U.S., given how people feel about nuclear power today, we couldn't build a reactor that it wasn't obviously much more safer than the light water reactors we've built in the past. Are there reasons to believe that a molten salt reactor would be substantially safer? Or one is you consider that would be also be cheap?
Yeah, the question is, why would the molten salt reactor be safer than the light water reactor? First thing I would say is that the light water reactor accidents have generally been few and not quite as devastating as you might think beyond the Chernobyl issue. So compared to other energy sources, the nuclear power to date has been quite safer in terms of loss of life. So it's a good source. The molten salt reactor is designed with all the experiences people have had about passive safety and so on. So again, it isn't so much that it's molten salt, it's that molten salt enables good engineering with fewer systems and able to achieve the passive safety that's needed. So, you know, we won't know until we actually build them and test them thoroughly. But I would say universally the people who are designing these believe that to be absolutely correct. Please.
Let's say that in 10 years the people doing ITER finally have a breakthrough and they achieve net positive fusion energy. How would you compare the liquid fuel fission reactors to potential, say, a tokamak design fusion reactor? Do you think we would actually have a world with both of those, or do you think that if fusion never comes, it will end up just supplanting all the fission designs?
Well, I think if fusion comes, great, but it's going to be quite a while. In any case, the tokamak designs are still, people are working hard on. There's a big project, ITER in Europe. We have that facility in California. And then we also have private ventures in New Jersey using, what do they call it, non-neutronic approaches, proton on beryllium, I think. So there's some potential for something to happen there. Most people don't think it's going to happen, but if it does, wonderful. If we have two sources, great. I don't see the downside to fission that a lot of people do.
You mentioned that the molten salt reactor is less conducive to proliferation. I didn't quite follow why.
I didn't cover that in the talk, but there's been a lot of comments that have been a bit overstated. People say, oh, you can't make a bomb out of it, and this and that. Well, you know, you can't make a bomb out of a light water reactor. It sits there like a plant. But if you have the technical skills, like they did in India or South or North Korea and so on, you can figure out how to make a special kind of nuclear reactor that generates, say, either plutonium-239 from uranium-238, or generates uranium-233 from thorium-232. You can do that by building a special purpose reactor to build material for nuclear weapons in both cases. Now, the hang-up with the thorium-uranium cycle is that it also creates uranium-232, which is a hazardous material in the sense that it decays quickly and is likely to injure or kill the people working on the weapons fabrication. So it's a little harder to use the thorium U-233 cycle to build nuclear weapons that way. So, so I would say the denatured molten salt reactor is highly proliferation resistant, but nothing is, you know, anyone with enough money and enough technology, enough science could do that. But the other evidence is that the U.S. did try to build a U-233 weapon way back, I don't know, 40, 50 years ago. And they did one test and they were unsatisfied and never did it again. So that's the only technical evidence I have for it. So the answer, again, in summary, is you can build a nuclear weapon out of almost anything if you have all the skills and money and expense. But even developing nations like India, Pakistan, North Korea, and so on, were able to build nuclear weapons with the technologies that exist today. So my suggested hurdle is that you only build reactors that are no more proliferation resistant than what we have today. That is, we don't want to increase the probability that someone can build a bomb, but we can't eliminate it because we have all these paths that are there already. Please.
You showed a table of costs that compared various forms of energy as actually produced today in real plants, and then compared this thing that we don't yet do that you'd like us to develop. So I'm curious how they compare to a few other technologies that we don't yet do today, but people want to develop in wind and solar and other renewables.
Your question is, what other technologies are there that I ought to be looking at in that table? Is that the question?
Yeah, like most of those were today's cost, and then you added this one at the end, which is here's one we could develop, and I wonder how it would compare to others that you could add.
Well, you're talking about things like hydro, for example. I didn't put hydro in the table because we really can't expand hydro very much. It's a nice source. It's relatively inexpensive. It's not very polluting. It's renewable. It's green. It's good. But there aren't too many sites left to do a lot of hydro. Geothermal I didn't put in because it's not that expandable. There aren't that many sites where you can get enough geothermal energy out. So I tried to pick just the examples that I thought would produce enough electricity to make a difference.
Sure, no, that's not exactly the question. The question is, here's the cost of wind as done right now. Here's the cost of solar as done right now. Here's the cost of nuclear as done right now. None of them do it. Okay, here's the cost of a different way of doing nuclear that could be cheaper. But isn't there a different way of doing, solar that could be cheaper that people could also develop within a decade? Are there things like that on the horizon? How do they compare?
I see. The question is, why didn't I sort of project the future cost of wind and solar and see if it might not be cheaper? And like I said, I haven't got a good answer to that, except to say, for example, in the case of solar power, it's pretty clear right now that photovoltaic is going to outrun the concentrated solar. It's going to be less expensive. And there is a lot of improvement in the cost for photovoltaic panels. It's down now to $1 a watt for the panel. But the panel is only a part of the plant. And so the costs for the mounting, for the heliostats to follow the sun, all those kind of things brought the costs up to the numbers I've suggested. So maybe there's some opportunity to reduce costs there. But again, in the case of solar and wind, we also have the storage problem. We don't have energy storage. So that we need to have some kind of backup power at all times for those. Okay.
I gather, like, as an unstated conclusion of the talk, that somehow what's going to happen in the future is that China is going to actually develop this technology and start selling it back to us en masse, right? Like, here's your 2-ton, power generation thing you can buy for this much, and here you have it, right? And we'll get it here, instead of having developed here in the States. Right?
Well, you're right. And China has been notorious at capturing intellectual property. And in the case of the Westinghouse arrangement, Westinghouse is building 4 AP1000s in China, but China required Westinghouse to surrender all IP to that product. And the deal they have is that China is allowed to build power and export power plants that are 1.4 gigawatts and up. So the AP1000 is a Westinghouse product. The AP1400 is a China product. So they have the rights to do that, and they intend to, I think. In fact, one of their power companies just went public. So the same thing would happen with the molten salt reactor.
Is that an issue that could be pointed out to politicians to actually make it easier? In the sense that there is an energy race, an energy technology race happening, and unless, similar to the space technology race, right? That kind of could facilitate new laws and regulations to make this go forward.
So, but I didn't quite understand the question. You said there's an analogy between the technology race and the energy race, but what is the question more?
Is that something, is that a simple message that could be sold to politicians as a reason to change regulation? Is that being tried?
I'm trying. I have a whole another topic I've been working on called Radiation is Safe Within Limits. And at the end of the talk, you can pick up one of these little brochures. I'm trying to get the public to understand the difference between the real harm from radiation and the regulatory rules that deal with it. But I don't quite know how to get the politicians to agree yet.
So I think the thrust of his argument is that the thrust of your talk seemed to be very fatalistic. China's going to do it, and that's the end of it. Without any exhortation that we should do something to try to change that, which is, I think, perhaps we all expected to hear.
Somebody's going to, sorry, if somebody, in China or anyplace else is going to invent this reactor and it's going to work and it's going to be cheaper than coal, when they take over the world, why not be optimistic?
Right, good point. If we're trying to solve the world's CO2 problem, does it matter whether China solves it or the US solves it?
The reactor with which I am somewhat familiar is the research reactor at MIT. And they're routinely getting SPRAMs, shutdowns, emergency shutdowns, due to various monitoring glitches and all sorts of things that do it for tests. And the model that you showed a sketch of is dumping a liquid only when hot fuel into a tank for it to solidify in, as far as I can tell. It seems that would be burdensome to go back into operation after such a shutdown. Is that something that, as far as you know, has been looked at?
Sure, they're looking at all that. I'm sure that the design would try to keep it warm. First of all, it has a lot of fission product decay heat. It's going to take a long time before that salt would get cool enough to actually become a solid, and you'd probably want to have some external heating there to keep it from getting solid, because it'd make it hard to restart with solid salt in all the pumps and things. So it could be quite a problem.
The answer is you pull off the cap whenever safety is established and dump it back into the reaction chamber effectively?
Well, you have to repump it. If it all solidified, I don't know how you'd get it restarted. But yeah, those kinds of issues are up front with all the people who are working on those projects.
Bob, so did you mention that China is spending, what, some $100 million a year or more building this design reactor?
This design reactor has a budget of $350 million for the first 5 years. And that was up until a few months ago, when it was given a new spike of funding that I don't know what it is, with the objective of speeding up the development. I don't know what the answer to that is. We could learn. Jiang himself is going to talk at the American Nuclear Society meeting in Reno. I think it's next week. Please.
I saw an article in Wired magazine a couple of years ago that really excited me about this stuff. And one of the things they talked about was, well, at least when I see nuclear plants now, they're all right next to the ocean, they're above ground, they've got giant cooling towers. And they kind of mentioned that they're kind of big terrorist targets. Like if terrorists had a bunch of planes and they crashed them into all our power plants, they'd be kind of out of luck for a long time when they went there. And they mentioned that some of these thorium reactors, maybe the molten salt cooled ones, they could be buried, which would sort of protect them from like airplanes, I guess. But they also mentioned that they can be made smaller, like each city could have one, and sort of keep it buried and run for kind of a long time, just kind of seal it up and use the power for a long time. Are those two benefits of these? Can they be buried and can they be much smaller?
Yes, the question was, how do you protect these kinds of plants against terrorist attacks from airplanes and so on? Can they be buried? And the answer ever since 9/11 is that people are very concerned about that. So even the AP1000 reactor design is capable of withstanding an aircraft crash. It won't collapse the dome, nor the big tank of water that's at the top of it. Many of the small modular reactor designs, like the one being built or proposed by NuScale or by BW, are designed to be underground power plants for that kind of reason. And my co-author Ralph Moore had a paper with Teller that designed and showed an underground molten salt reactor plant. So yes, they can be underground, and that seems to be the strategy that a lot of new reactors are going to follow.
And smaller reactors, right?
And smaller reactors, yeah. I'm proposing smaller reactors principally, well, a couple of reasons. They're easier to cool in a situation where you have no external power, like we had in Fukushima. They're cheaper. There's less investment up front, less risk capital for the utility for the first 2 or 3 of these plants. and because you get the benefit of mass production. We have a big engineering controversy constantly going on about economy of scale in bigger and bigger plants, but the bigger plants sometimes bring new problems to bear. So if you give up economy of scale, you also get in return the economy of the learning curve because you're going to produce more units. So I think the smaller units are going to win out. Go ahead. Sure.
Yeah, Bob, quick question on your chart showing the cost per kilowatt hour of the various alternatives. Is there any attempt to include the transmission costs, or are transmission costs not relevant?
I did not include transmission costs. They can make a difference if you are thinking about powering the U.S. with renewables from long-distance power sources. Something like, figure a penny a kilowatt hour per 1,000 miles of high-voltage DC transmission. Keep that number in the back of your mind when you're trying to design these things. Please.
Right. Is the nuclear waste produced by these plants different in some sense than waste produced by light water reactors?
Is the nuclear waste different than the waste produced by light water reactors? Yes, quite different. The light water reactors waste is in the same fuel form it went in, so fuel rods that are then to be disposed of at some future undetermined place. The molten salt reactor can continue to operate and consume a lot of the so-called actinides, the heavy uranium, the heavy elements like plutonium, americium, californium, and so on. So the long-lived heavy metal radioactive products continue to be consumed. Now, when you finally stop the reactor, you're going to have some of those left. So the amount of that waste per kilowatt hour that was generated is lower, but you're still going to have that kind of waste to deal with at some point. In addition, both kinds of reactors generate the fission products. That is the cesium or iodine or whatever it is, or xenon and strontium and so on that you've heard of, which come from splitting those big heavy nuclei of uranium and plutonium. Both kind of reactors generate the same kind of fission products, but the decay time for those is on the order of a few hundred years before they're really more or less benign for handling. So the answer is there's less of the waste per kilowatt hour generated, less of the long-lived waste per kilowatt hour generated, about the same amount of waste per kilowatt hour generated for the fission products that have the more shorter lifetimes.
So if we were to say try and replace as much of the coal and natural gas power infrastructure with liquid thorium reactors instead, how much would we still need in the mix to provide peak and on-demand power? Because I'm assuming even the smaller thorium plants won't be able to come up on demand to respond to the grid.
Yeah, the question is, would you need some kind of peaking plants in addition to the nuclear power plants because they're slow to respond to demand changes? Well, the current plants are slow basically because they were designed that way. They could have been designed to be more responsive, but they haven't. They are designed to recover all their costs at full power. So the owners of those plants don't want to turn them down. Now, the newer plants will have the same issue in the sense of, can we, do we want to turn them down? The owners will say, no, I want to keep generating money. So that's the real issue. You can engineer it to make it go, turn it down pretty easily. The plants do what's called load following. That is, if you diminish the load on the power plant by turning off the lights or breaking a power pylon and ruining the load on the plant, the ability to dissipate heat disappears, the temperature of the reactor goes up, and the physics of the reactor design shuts it down or slows it down. That same principle means that it automatically does load following. So you can indeed have these plants run at a lower speed and not require backup from, say, natural gas or something like that. Oh, thank you.
Thank you.